All right, my name is Russell Lane, and I am presenting nitride nanoparticles. And let's see, to start off, what are nanoparticles? We can think of pretty much any nanomaterials as being materials with overall dimensions on the nanoscale, pretty much less than 100 nanometers. In the recent years, nanomaterials have become more important in many applications from medicine all the way to aerospace, a lot of the insulating coatings they put on. Uh, and it's not just the size that distinguishes these nanomaterials, but also includes their chemical reactivity, energy absorption, and biological mobility. And nanoparticles can also be organic and synthetic. Now, a little bit about the history of nanotechnology. Um, it's been around for a while, but the modern field we think of when we hear nanotechnology kind of got its start in 1980s with the invention of the tunneling microscope, which allowed scientists to actually see individual atoms. And before this, though, there was speculation on how science would start evolving to utilize nanoparticles. And this began with Richard Feynman, and he gave a talk in a American physicist lecture. Well, he's an American physicist, and he lectured. There's plenty of room at the bottom. And this was at American Physical Society meeting at Caltech on December 29th, 1959. And this was thought to have provoked and inspired the field of nanotechnology. As well, for the people that invented the tunneling microscope, they won the Nobel Prize in 1986 in physics for inventing that scanning tunneling microscope that really just added the substance to the field of nanotechnology, enabled us to progress. And IBM actually uh, did a famous thing where they actually used individual atoms and spelled out IBM. So that was pretty cool. And then we have Norio Taniguchi, and he was a Japanese scientist of Tokyo University of Science, and he was the first person to use the term nanotechnology. So he coined that term that we're all so familiar with now, and this was in 1974 conference to describe semiconductor processes. And so even all the way back to the 50s, they were speculating about this. These were our scientists, but the first nanotechnologists were actually goes back all the way to BC days, and we can think of they may not have known what was going on the nano level, but they were definitely able to utilize natural nanoparticles, and this we can think of this included carbon nanotubes found in India around 600 to 300 BC, with the cementite nanowires found in Damascus steel around 980, and nobody knows actually how Damascus steel was made or really where it originated. Um, and then we have artisans in Mesopotamia and medieval Europe who utilized metallic nanoparticles for the gold glittering effect that we find on a lot of chalices and everything in different ceramics. And a lot of this came from the Muslim world because they weren't actually allowed to use gold to add that color. So yeah, to get creative, and they utilize these different things, and it kind of carried on to the medieval Renaissance period. And looking at this cool timeline, but I'm going to move on past this. But I thought this was really cool, showing pretty much the use of nanoparticles throughout history, starting with all the way from the beginning in the Big Bang, and it goes all the way up to the Satsuma glass. Now, we can think of the classifications of nanoparticles. Well, nanoparticles are classified into organic, inorganic, and carbon-based. So, further classification by their morphology, size, physical, and chemical properties. And we can think of organic nanoparticles as composed of organic compounds such as lipids or polymers with a diameter in the range of 10 nanometers to 1 micrometer. And these are really utilized in medicine and become more prominent in the medicine field for especially drug delivery. We can think of examples of these as dendrimers, liposomes, micelles, and ferritin as organic nanoparticles. Now, inorganic nanoparticles, these aren't made of carbon. Um, these are the metal and like say metal oxide nanoparticles, metal nitrides. These are the inorganic nanoparticles. And some examples, moving our way down, I think gold, silver, copper, iron and zinc, and the synthesis of these metal-based nanoparticles due to the presence of a partially filled d orbitals makes for their heavy redox reactivity. And then we have metal oxides, some examples of these, which is the step further past just the mono element going on there. We have the metal oxides such as magnetite and iron oxide and aluminum oxide and silicon dioxide and titanium oxide. And then past these, we have carbon-based nano particles, and these are composed of carbon, guessed it. And these exist in different shapes, including tube, horn, spherical, ellipsoidal, and the two major classes of these are fullerene and carbon nanotubes. And the other classes also include graphene nanofibers and carbon black. So now let's think this is like a general synthesis of nanoparticles. So the two main approaches for synthesizing nanoparticles we can think of as including a top-down approach. And this is pretty much breaking down bulk material into nano-sized particles. And this is a destructive method. And example methods include mechanical milling, nano lithography, laser ablation, sputtering, and thermal decomposition. Now, a bottom-up approach, this is a constructive method. And nanoparticles are built up from clusters obtained from atoms. And these techniques include sedimentation and reduction and more economical and less wasteful. These methods include sol gel, spinning, green synthesis, chemical vapor deposition, uh, pyrolysis, and biosynthesis. So these are the two different general synthesis approach for creating nanoparticles. Now, looking at this is getting into the nitride nanoparticles. So now we're not just general nanoparticles, this is going on for the nitride. So the properties of these nitride nanoparticles are most nitrides can be characterized as high temperature materials that show high mechanical strength, and they're usually superconductors and dielectric. They show chemical resistance, which is why they're used a lot, low density and low coefficient of friction. And unlike traditional nitrides, such as ceramic structures that a lot of the nitrides were used for, a lot of the ceramic things, the synthesis of nitride nanomaterials needs highly accurate control to guarantee target nanostructure phase purity, which makes the whole synthesis, still a challenge to achieve. But widespread attention for applications in renewable energy to novel electrochemical activities along with high chemical stability. So as well, higher thermal stability and resistance towards oxidation compared to the carbon nitride nanoparticles. These are so the metal nitride nanoparticles have this high thermal stability compared to the carbon nitride particles. Non-stoichiometric interstitial compounds with large free carrier concentrations. Once again, this is the metal nitride nanoparticles. And examples of these include titanium nitride, zirconium nitride, tantalum nitride, and hafnium nitride. And a lot of these metal nanomaterials are very important, and they go along with use with silicone and CMOS technology, and they're used as barrier layers in copper, Damascene process, as well as gate metals to N-type and P-type transistors. And main metal nitrides offer this fabrication and integration advantages with plasmonic and nano electronics. Now, metal nitride structure, there is a bunch of different variety of these crystalline structures, and this diversity includes nanopyramids, core shell, nanopore sheets, nanoflowers, quantum dots, nanotubes, nanoflowers, nanocubes, nanorods. And a lot of these, they're similar in structure to the transition metal carbides nanomaterial. And just a couple of these ones, say titanium nitride, for example, they have like a rock salt structure consisting of these interpenetrating face cubic center metal and nitrogen sublattices. Um, and yeah, this titanium nitride shows this cubic structure. It's just like sodium chloride type, metallic, and conducts electrons like table salt. Now, titanium nitride, I thought this was kind of cool to put in here. Titanium nitride with a 3-to-4 ratio. So when you have more of the nitrogen compared to the titanium, it's this semiconductor composed to a 1-to-1 ratio of titanium nitride. And this allows it to turn on and off its electrical connectivity. So this is tremendously important in electronic devices. So this semiconductive state is achieved by a band gap, which requires certain energy to initiate electrons moving from lower energy insulating states to higher energy conducting states. And we can see here these two diagrams or figures on the right. The first one in that cube shape, that's going to be the titanium nitride. So that's just the 1-to-1. That's the basic titanium nitride. Now moving down, discovered actually recently, I believe, or a couple of years back, this is titanium nitride, but with that different stoichiometric ratio with the 3-to-4. And that completely changed its ability to turn it into a semiconductor, which just expanded its whole use into electronics. Moving on, now we have the different synthesis methods for these nitride nanoparticles, and there is a good amount of different synthesis ways of creating them in the start. So nitrides are generally synthesized under high temperature, and these temperatures are usually around 800 to 1500 degrees Celsius, and usually along with high pressure to obtain these nitride materials with bulk or ceramic structures. So in order to obtain nano structured nitrides, active precursors such as halide active precursors material would be selected along with active intermediates. And these active precursors, I included a couple examples in these active intermediates. And moving on, just going through the different syntheses, we have chemistry. vapor deposition, self-propagation, high temperature synthesis, solid state metathesis reactions, and solvothermal synthesis. Now, this is kind of really cool. A lot of the nitrides before now, with the booming nano industry and the heavy investments in commercial and research alone, we're starting to see more of these. But nitrides used to just be these bulk, in industries, bulk and these ceramic things that we'd make. And it's showing the two different synthesis. So we have the self-propagation high temperature synthesis and this solid state metathesis. And these are usually not made for making these nanomaterials, but these just bulk nitrides. And then moving on, all of them in like the orange red, we have the nanostructured nitrides, and we have all these different synthesis reactions going on to create these different, everything from different shapes to whatever we need for the nitride nanomaterials. So breaking them down, to start, we have the SAHS method, which is the self-propagation high temperature synthesis. And initial reagents are essentially spontaneously transformed into products due to the insanely high, the exothermic heat of reaction once ignited. So once it gets going, it's going. Fast release heat from exothermic reactions, combustion temperature is short, and the conversion rate to product is high using this method. This is a practical method for large scale preparation of nitride powders. But using this though, so it's good for making a lot of these bulk nitride powders. And looking back, you can see it in one of the first ones. So it's not exactly geared towards, started off just for nitride materials. It wasn't used for these nano materials. So that's why it's used for making just a lot of nitride powders, but it's difficult to achieve a controllable preparation of nitride nanomaterials. Yeah, and you can see that right here is an example of the synthesis in super high heat with 1050 degrees Celsius. And essentially you have these alloy powders under just continuous flow of nitrogen until that high heat enables the reaction to create those nitride powders. Now, moving on, we have the solid state metathesis reactions. And these are widely used to produce bulk and nano-sized metal nitrides. Revolves around the replacement reaction between metal halides and alkali earth metal nitrides, such as lithium nitride and sodium nitride, yielding metal nitrides. The high pressure confirmed in the solid state metathesis benefits the contact diffusion and ion exchange of the solid reactions. And well, crystallized, nanomaterials via high pressure solid state metathesis enables the solid state ion exchanges and nitrogen pressure of super high pressure. It enables the reaction to perform even better, creating these nanomaterials. And then we have a chemistry vapor deposition. This is favored by chemists and physicists and material scientists for creating thin layers of geometric nanosheets, nano column, or nano flowers. And these are fabricated by heating volatile metal halides under this just constant flow of nitrogen gas. And this method is occurring in high temperature. And you can see here an example, the nitrogen gas right there. And this high temperature that enables this replacement reaction of the metal chlorides by metal organic salts actually using metal organic salts could reduce the reaction temperatures to this. So if you use metal organic salts in this reaction, you can actually get away with using a lower temperature due to the reactivity. Now we have the solvothermal synthesis of making these nitride nanomaterials. This is carried out in organic solvents within a autoclave. And under certain temperatures and autogeneous pressure where solvents dissipate, the enthalpy of exothermic metathetical reactions and reduce the diffusion barriers between reactants. And solvothermal reactions occur at a relatively low temperature compared to the other methods that we were looking at, synthesis methods. And it provides so now we're getting a lot better control of our size of our nano products and the morphology of the particles compared to the solid state reactions. Now, those are all, this is all relatively new, but now we're getting into even more new synthesis methods. So all those you can think of as more traditional nitride synthesis reactions. Now, looking at these novel ones, we have the nanocrystals. Well, here's the benefits. The nanocrystals are easily obtained from additive synthesis. Now, these include ammonolysis, molecular precursors, sol gel method, and salt melt synthesis. Additive assisted synthesis, so breaking it down, this is based on that solid state method and the solvothermal reactions. And especially it's aiming for it's selecting thermodynamically spontaneous reactions and raw materials with high activity. So it's just a really smart way of choosing your precursors to make these nanoparticles. Then we have a monolysis, and this is a temperature programmed. Monolysis involves heating a metal oxide in this flowing nitrogen gas and slowly raising the temperature. And you have these crystallographic orientations, particle size, and geometry are all retained from reactant solid. So this monolysis, you can think of it as just this very careful synthesis reaction where that precursor, that metal that you're using in the beginning, that reactant solid, is going to retain a lot of its geometry. And then we have the molecular precursors method. And this is nitrogenous precursors are firstly synthesized. Then the precursors would follow by low temperature decomposition and a high temperature calcination through which the size and morphology of the nanocrystals can be controlled by adjusting the temperature and the heating time. Now, looking at some more of these newer synthesis methods, we have sol gel processing. And this is widely used now for producing nitride nanomaterials, such as we had nitride powders before and those solid state ones. Well, this is nano powders now, or it's specializing in nano powders or nanoporous structures. Molecular precursors are formed in solution and then heated to yield a gel and fired to the target nitride. So this is how we're creating this gel. And now we have this salt melt synthesis. Now this is a very special one. This is a special synthesis where the reaction takes place in molten salts, and the products are obtained through washing the cooled salts when the reaction is completed. And the advantage of this include lower synthesis temperature, shortened reaction time, size, morphology of the nitride nanoparticles, and this can be really well controlled under these lower temperatures. So the way you can think about this, it kind of seems, the reactions that make use of low temperature or a slowly increment increasing temperatures, you generally get more control. It's not as happening as fast. You get more control of your nano product. And then we have the microwave synthesis, which is rapid heating. But you have to remember, this is not just like a hot temperature. This is microwave, which is allowing you to heat it evenly. So this is why you see this homogeneity and selectivity. So this deep penetration into the substance. It's quick, so you get the benefit of that high heat, those high reactions, but you also get the benefit of the low heat ones, even though this is happening in a fraction of the time of the other methods utilizing these microwaves. So it takes a fraction of the time the conventional methods to complete the entire heating process. And nitride products are small and distribution is uniform. So this is very precise synthesis method right here. Applications include electrochemical devices, environmental remediation. So the applications of these nitride nanoparticles really extend into electrochemical devices, environmental, helping out the environment, gas sensing, photocatalysts, applied ceramics, of course, because that's where nitride's really had its start in ceramics, but hard coating, cutting materials, insulators, very important in the aerospace industry. Moving on, these coatings they provide, why are they used? They provide corrosion resistance, heat resistance, and wear resistance. And optical properties of these nitride nanoparticles and are based on the reflection, the transmission, light emission, all dynamically different than their bulk material, the bulk nitrides. And this they're being increasingly used as photocatalysts and battery material. Increased flexibility and reduced cost of electronics is the end goal of utilizing these novel, nitride particles. And so now they're synthesizing these nano nitride crystals from all these range of methods now. And the end goal is to make these components of these electronics even cheaper and more efficient. So nitrides are and increasingly nano nitride material are becoming more important in the materials. Now, nitrides are very important already in our infrastructure of LED lights, but they're getting even more so with the increasing ability to make these different size nanoparticles of these nitrides. And this is very important for the green, blue, and UV light emitting devices. So nanostructures consisting of nitrides of gallium, aluminum, and indium nitrides are some of the most important building blocks for semiconductor technology involving micro LEDs to increase their brightness and energy efficiency. And this is accomplished by having this ideal proximity to the band edge, which enables these nanonitride materials to be suited for these microelectronic applications. And I thought this is pretty cool. I included here. These are the different applications of these nitride nano particles. And you can see here, and it's water splitting, solar cells, supercapacitors, batteries. A lot of people don't think of that, but those are a lot of times a lot of these nanonitrides are used. And health risks, though, it's important we talk about this because, well, anytime, there's already worry about nanoparticles since we essentially are making something, and even the natural ones, they have, when it's so small, it really easily gets into your body. And it can do that in any numerous amount of ways. When you look at, say, the middle figure, you can see how the nanoparticles are internalized in cells. There's definitely some risk. Nanoparticles pretty much make their way into every part of your body. So as we're increasingly utilizing this technology, we're going to have to be more careful. And especially when we're thinking about these nitride ones, they're starting to be used for more and more of everything. So it's important we stay aware of the risk, and the mechanisms underlying the toxic effects of nanoparticles are complex. So it's not even just sometimes the size, it's the different reactability and all the things that come with them being at this nano size that enables all these more different things we don't understand yet. Various factors such as shape, size, surface chemistry, and physiochemical properties of these nano materials. Several studies have even shown that their toxicity of nanoparticles is mainly due to their ability to generate these oxygen species that are highly reactive. So they cause oxidative stress. These ROS particles are highly reactive molecules that can damage cellular components such as proteins, lipids, and DNA, leading to cell death or dysfunction. And toxicological mechanism is complex and multifactorial. So development of, all these biocompatible nanoparticles is crucial for their successful application. So, as we're developing these, we're going to have to develop a highly regulated, and healthy way of dealing with these things, so we can, as our infrastructure builds on nanoparticles, we don't die. So, all right. So yeah. And moving on, citations. All right. And that is my presentation on nitride nanoparticles. All right. Have a good one.